Look out of an airplane window, and the first thing you notice is usually the view. The clouds, the wing. The strange feeling that you are sitting in a room thousands of feet above the ground. But before that window ever shows you the sky, it has to do something much more important. It has to survive the airplane. Because an airplane window is not just a piece of glass in a wall. It is a carefully shaped opening in a machine that is holding back invisible pressure. And that shape, that small, rounded edge, is not a decoration. It is one of those quiet aviation details that exists because engineers learned exactly where trouble likes to begin.
That feels like a tiny detail for a very expensive machine.
It is, and the reason reaches deeper than most passengers realize. To understand it, we have to talk about thin air, cabin pressure, metal that weakens over time, and one of the most important lessons of the early jet age. To understand the window, we have to zoom out to the airplane around it. At cruising altitude, the air outside the aircraft is thin. Not because the air suddenly has a different recipe, but because there is less pressure holding those molecules close together. Your body depends on pressure to help move oxygen from your lungs into your blood. So if an airliner simply let the outside atmosphere into the cabin at high altitude, the view might be beautiful, but the passengers would not be okay. That is why the airplane creates a controlled pocket of air inside the fuselage. The cabin is pressurized, meaning the air inside is kept at a higher pressure than the air outside. And that pressure difference changes the job of the aircraft body. The fuselage is no longer just a tube carrying passengers. It is also a structure holding back an invisible force. So the plane is basically carrying a tiny atmosphere, rude of physics, but efficient. Every flight adds this pressure load. Climb, pressurize, cruise, hold it, descend, release it. One flight is manageable, but airplanes do not fly once. They do this again and again and again. Which means the shape of every opening in that pressurized shell matters, especially the window. Now, imagine the airplane's fuselage as a smooth sheet of metal wrapped into a tube. When the cabin is pressurized, that tube is being gently pushed outward from the inside. The metal skin, the frames, and the supports all help carry that load. But passengers need windows, so engineers have to cut openings into the structure. And an opening changes everything. Before the cut, force can spread through the metal in a fairly continuous path. After the cut, that path is interrupted. The load does not vanish. It has to go around the hole. This is the hidden design problem behind every airplane window. You want the passenger to see out, but you also need the aircraft structure to keep carrying force around the opening, flight after flight. So the window is not just judged by how clearly you can see through it. It is judged by how safely the structure can carry load around it. That is where shape becomes important. Here's the simplest way to picture stress. Stress is not a mysterious force hiding inside metal. It is the way a load is spread through the material. In a smooth piece of metal, that load can spread out evenly. But when the metal has a sharp corner, the path changes suddenly. The force has to turn. And when it turns too quickly, more of it crowds into a smaller area.
So basically, corners are stress traffic jams.
Exactly. A sharp corner can become a place where stress concentrates. That does not mean the metal instantly breaks. It means that spot is being asked to do more work than the metal around it. Now compare that with a rounded opening. A curve gives the load a gentler path. Instead of bunching sharply at one corner, the stress is spread more gradually around the edge. This is why curves show up again and again in engineering. Not because engineers dislike straight lines, but because nature is very good at finding weak spots. And in a pressurized airplane, a window corner can become one of those weak spots. A rounded window does not make stress disappear. It helps manage where that stress goes. And when the same airplane pressurizes and depressurizes thousands of times, managing stress is not a small detail. It is the beginning of the safety story. This is where the story becomes more serious. In the early 1950s, the de Havilland Comet represented the future of passenger flight. It was fast, smooth, pressurized, and designed to fly higher than the propeller aircraft most passengers knew. But the Comet was also pushing aviation into a problem the industry did not yet fully understand. A pressurized jetliner does not only have to be strong once, it has to survive pressure cycles over and over again. Climb, cruise, descend, repeat. After Comet accidents in 1954, investigators faced a difficult question. If the aircraft had been tested, why were production airplanes failing much earlier than expected? To investigate, engineers placed a Comet fuselage in a water tank and repeatedly pressurized it, using water so the test could be controlled more safely. The fuselage was cycled like an airplane living many flights in fast motion. One especially important detail was that an earlier test fuselage had been pressure tested above normal operating pressure before later fatigue cycling. That high pressure test unintentionally changed the metal around the most stressed areas, so the test specimen did not behave exactly like production aircraft in service. That is the haunting engineering lesson. You can test the right thing in the wrong condition, and the answer can still mislead you. The Comet story forced aviation to take fatigue and stress concentration around openings much more seriously. And yes, window shape was part of that lesson. Modern airplane windows are rounded because engineers do not want stress gathering at sharp corners in a pressurized fuselage. But the curve is not a magic shield. It is one visible piece of a larger safety philosophy. Design carefully, test realistically, inspect repeatedly, and never assume tiny cracks are harmless. The Comet story is not a punchline about bad windows. It is a reminder that aviation safety often advances when engineers learn to see what passengers cannot. Pressure, fatigue, crack growth, stress concentration, forces that are invisible until the structure reveals them. And that is why the tiny curve matters. And that brings us back to the window. If a corner is where fatigue likes to begin, then the shape of that corner matters from the very first design sketch. Fatigue is one of the strangest ideas in engineering, because it does not always look dangerous at first. A piece of metal can handle a load once and look completely fine. It can handle it again and still look fine. But repeat that load enough times, especially near a high-stress detail, and tiny damage can begin to grow. That is fatigue. Not metal getting tired like a person gets tired. More like a paperclip being bent back and forth. One bend is not the whole story. The repetition is. On an airplane, the repeated load comes from the rhythm of flight. Each cycle is small compared with the strength of the whole aircraft. But fatigue does not need the whole aircraft to be weak. It only needs a place where stress is higher than the area around it. A sharp corner, a small hole, a manufacturing detail, a tiny flaw. Once a crack begins there, each new pressure cycle can help it grow a little farther. So now we can finally answer the original question more completely. Airplane windows are rounded because a pressurized aircraft cannot afford sharp corners where stress can gather. A rounded or oval window gives the load a smoother path around the opening. The curve spreads the stress more gradually instead of forcing it to crowd into a tight corner. That does not make the window stress-free. It makes the stress easier to manage. And that is the real job of the shape. The airplane still needs glass, seals, frames, fasteners, reinforcements, inspections, and pressure control systems. The window is part of a system. Modern aircraft design does not rely on one lucky detail. It layers safety.
Tiny curve. Surprisingly large responsibility.
And that is what makes it such a beautiful piece of design. It solves a structural problem so quietly that most passengers mistake it for a style choice. But hidden inside that curve is a century of engineering discipline, pressure, fatigue, testing, and respect for small details. The window is small. The forces around it are not. This is the part of aviation that passengers rarely see. The things that make an airplane safe are not always dramatic. Sometimes they're almost boring. A radius, a reinforcement, a test cycle, a maintenance checklist. But boring is often where safety lives. The rounded window is a perfect example. It does not shout for attention. It does not explain itself. It just quietly changes how force moves through the aircraft. And once you see that, airplane design starts to look different. So the next time you sit by an airplane window, you may still look at the clouds first. That is the whole point of a window. But now, maybe you will notice the shape around the view. That small curve is not decoration. It is a quiet answer to a difficult engineering question. A square corner asks the metal to handle stress too abruptly. A rounded corner gives that stress a smoother path. And in a machine that repeats the same pressure cycle thousands of times, smoother paths matter. That is the hidden beauty of airplane windows. They turn an invisible force into a visible design choice. They remind us that safety is often built from details most people never think to question. So thank the tiny curve.